lesson. So let's jump into it. So it says, why are we able to see? Because there is light. But what is light? Light is a form of a wave. So what is a wave? A wave is a disturbance that carries energy from place to place. A wave does not carry matter with it. It just moves the matter as it goes through it. This is a big misconception with students, is that they think waves moves matter, but it just vibrates the particles as it's moving through. Some waves do not need matter, called a medium, to be able to move, for example, through space. These are called electromagnetic waves, or EM waves. So make sure you know that abbreviation as well. Some waves must have a medium in order to move. These are called mechanical waves. So we're going to talk about the difference between electromagnetic waves and mechanical waves. There are also different wave types. The first one is transverse waves, waves in which the medium moves at right angles to the direction of the wave. So here's an example of what these would look like. So you can see if there is the initial position of those particles, and as the waves are being moved, you can see that there is a curve obtained by joining the displaced particles. So we have different vocabulary words that you need to know about a transverse wave. A crest, which is the highest point of the wave, and a trough, which is the lowest point of the wave. So another way to look at it is a crest is the top of the mountain, and a trough is the valley of a mountain. Next type of wave is compressional or longitudinal waves. These are waves in which the medium moves back and forth in the same direction as the wave. So they're going to be moving forward and backwards, as you see in the arrows of the direction of the wave, as the vibration of the particles are moving. So you can kind of think about this as a spring. So a normal position of the spring, and then you have compressions and refractions based on that wave as you are pushing or pulling that slinky. Another way to visualize a compressional wave could be with the dots. So you can see compression is where they would be closer together, and the refraction is where they would be spread apart more. So there are different parts of longitudinal waves as well. So compression is where the particles are close together, which we saw in those pictures on the last slide. Refraction is where the particles are spread apart. So again, the compression is where they are closer together, and the refractions are where they are spread apart. Here are some wave properties that you should know as you move through the unit. Wave properties depend on what type of energy is making the waves. So the first one is wavelength. This is the distance between one point on a wave and the exact same place on the next wave. So this would be an example from trough to trough or crest to crest. So that would be a measurement of wavelength. For a compressional wave, it could be where it's refraction to refraction or compression to compression. That also would give you the distance or the measurement of a wavelength. Frequency. This is how many waves go past a point in 1 second. Unit of measurement is in hertz, and this can be abbreviated with an Hz. The higher the frequency, the more energy in the wave. 10 waves going past in 1 second would equal 10 hertz. So here's going to be some mathematical problems that you might come across in the module. Another example is 1,000 waves go past in 1 second. It would equal 1,000 hertz. 1 million waves go past in 1 second would be 1 million hertz. So the third property is amplitude. This is how far the medium moves from the rest position, or where and it is when not moving. Remember that for transverse waves, the highest point is the crest and the lowest point is the trough. So again, the amplitude would be the mean position of the particle, so where the particles began at, to where they were finishing. So the amplitude would be from that middle point to the highest point of the crest, or the middle point to, or the initial point to the lowest point of the trough. That's how you would measure amplitude. Remember that for compressional waves, the points where the medium is close together are called compressions, and the areas where the medium is spread apart are called refractions. So again, I like to visualize the compressional waves as a slinky. So when the slinky springs are close together, that is going to be a compression, and when they're further apart, it's going to be a refraction. So the closer together and further apart the particles are, the larger the amplitude. So that was how you would measure the amplitude on a compressional wave. The energy of a wave is proportional to the square of its amplitude. So mathematically speaking, you have an equation E equals CA squared. Where, let's talk about the letters, E is going to equal the energy or the capacity to do work. C is a constant, depends on the medium, so that would be depends on the particles that the wave is traveling through. A equals amplitude. So here's an example. If the amplitude is equal to 3 units, and we assume C is 1 for this case, you can calculate the energy by substituting the numbers that was just given. So you would have 1 times 3 squared, so that would be 1 times 9. So the energy would be 9 units. Note that when the amplitude of a wave is 1 unit, the energy is 1 unit. So you can see the relationship between the amplitude and energy of waves. When the amplitude is doubled, the energy is quadrupled. So now you can see the exponential growth on the graph between amplitude and energy. When the energy is 10 times greater, the energy is 100 times greater. So note the relationship between amplitude and energy. The fourth property is wave speed. This depends on the medium in which the wave is traveling. It varies in solids, liquids, and gases. A mathematical way to calculate speed would be wave speed equals wavelength times the frequency. So again, you would measure wavelength in meters or some kind of distance times frequency, and again the unit for frequency would be hertz. Or you have V equals F times the hertz sign. Problem: if a wave has a wavelength of 2 meters and a frequency of 500 hertz, what is its speed? So the answer would be 1,000 meters per second in velocity. The next topic is changing wave direction. So we have reflections, which is when a wave bounces off a surface. If the surface is flat, the angle at which the wave hits the surface will be the same as the angle in which it leaves the surface. Angle in equals the angle out. This is the law of reflection. Refraction. Waves can bend. This happens when a wave enters a new medium and its speed changes. The amount of bending depends on the medium it is entering. A great example of this is why you see different locations of an object underwater. So look at the pencil to the right. You can see that it looks like the pencil is broken because the wavelengths of that light is refracted as it's entering a different medium. Then we also have diffraction, which is the bending of waves around an object. The amount of bending depends on the size of an obstacle and the size of the waves. Large obstacle, small wavelength equals low diffraction. A small obstacle with large wavelength is usually equaling a large diffraction. And that is it for the introduction to the wave unit. Again, please join my live session Wednesday night at 7 p.m. if you have any questions about this lesson, or any questions about the module or class in general. Thanks for joining in.